Today we'll be looking at application of derivatives and monotonicity. So these are the formulas for the length of the tangent, length of the normal, length of the subtangent, and length of the subnormal. So the y is the point at which you'll be checking for the length of the tangent or the length of the normal. So let's say you have to check it at the point x and y, and substitute the y over here, or like it's p and q, then you substitute the q. And how do you get the m? So we have the equation of the curve, which is y equals f of x. So m is simply dy by dx, so that's f dash of x. And you substitute the x value, or in this case the p value, into this to get the value of m. So that's how you get the length of the tangent and normal, subtangent, and the subnormal as well. Next we have the angle between two curves, which is basically the angle between the tangents at the point of intersection. So what does that mean? Let's say we have two curves. This is the first one, C1, and this C2. So you want the angle between them. This is the intersection point, right? So you find the tangent at this point of both the curves. So that's T2 for the curve C2, and that's T1 for the curve C1. So whatever the angle between T1 and T2 is the angle between the curves. So how do you find this angle theta? Basically, you have the slope of these tangents. These are just straight lines, so you can get the slope. That's m1 and that's m2. So how do you find the slope of the tangent? Obviously it's just dy by dx of this point substituted into the tangent equation of the curve. So we have the slope of the first tangent m1 and the slope of the second tangent is m2, and this is a formula you need to remember, that tan theta is m1 minus m2 over 1 plus m1 m2. You can see that this is really just the tan a minus b formula. So this is like a tan a and that's a tan b, and you need theta, which is like the subtraction of the slopes. So that's tan of a minus b. You just do tan a minus tan b over 1 plus tan a tan b. Next up we have orthogonality of two curves. So how do you check if two curves are orthogonal? Let's say that's their intersection point, and you have both the tangents T1 and T2 with slopes m1 and m2, and both the slopes should be equal to -1, just like we check for the perpendicularity of straight lines. So you just multiply the slopes and the product should be equal to -1. Similarly, at the intersection point you find the tangent equations and you multiply the slopes and they need to be equal to -1. Then you can say that the curves are orthogonal. And if you have 2 points of intersection for the curves, you have to check for orthogonality at both the points, and if the curve is orthogonal at both the points, only then you can say that the curves are orthogonal to each other. This condition needs to be satisfied at both the points. Next we have the shortest distance between two curves, and obviously the distance lies along their common normal. So what does that mean? Let's say we have two curves, C1 and C2, and these are the tangents. So the common normal to both the curves should be something like this. So basically, to these tangents T1 and T2, the common normal is perpendicular. The distance, or rather the length of this common normal, is the shortest distance between both the curves. And next we have also another thing. Obviously this is kind of obvious, but T1 and T2 are parallel. Next we have rate of change. Let's say with respect to x, rate of change of y is given as dy over dx. That's about it. There's a lot of questions on this though, so something you should keep in mind. Moving on to monotonicity. So what's a monotonic function? A function is said to be monotonic if it's increasing or decreasing in an interval. So for the interval minus infinity to infinity, so that's basically all of real numbers, monotonic functions would be e power x, e to the minus x, ln of x, a to the x, and straight lines mx plus c. All these will be monotonic functions as they're only increasing or decreasing in that interval. So e power x looks something like that, so it's only strictly increasing, e to the minus x is strictly decreasing, and ln x is once again strictly increasing, and a to the x is similar to e to the x, and obviously straight lines are either increasing or decreasing. That's a monotonic function. So what's a non-monotonic function in the interval of the entirety of real numbers? That would be something like a cubic function. So that's a cubic function, and it's not strictly increasing or strictly decreasing. It's increasing and decreasing and then again increasing. So that's non-monotonic. Okay. But if the interval given was something like minus infinity to this one, that would be a strictly increasing function. Or if it was minus infinity to here, that would again be a strictly increasing function. And from over here to over here, where it's strictly decreasing. And again, if the interval is from over here to positive infinity, that's again an increasing function. That's something you need to keep in mind. So this is actually a really important topic for both mains and advanced, and especially for advanced, which is increasing and decreasing functions. So for an increasing function, obviously the slope at any point is greater than 0, and for a decreasing function the slope is less than 0. However, this condition only applies to strictly increasing functions. So for a strictly increasing function, slope always needs to be positive, and if the slope is 0 at discrete points, so let's say just at some points, right, very few, far apart, even then you can say that that function is strictly increasing. So the conditions for a strictly increasing function are that firstly, the slope is always positive throughout the function, and secondly, if the slope is 0, it only needs to be at discrete points. At a few far away points, only then the function is strictly increasing. However, for a monotonically increasing function, the slope can be positive or equal to 0. I guess a better way to write that would be f dash of x is greater than or equal to 0. So that's a monotonically increasing function. Let's say that these are two functions. The first function is strictly increasing as its slope is positive at every single point. It is also monotonically increasing because the condition for monotonicity is that the slope needs to be greater than or equal to 0. Whereas the second function is not strictly increasing as the slope is 0 for a given interval. For a strictly increasing function, the slope can only be 0 at only a very few number of points. However, for a monotonic function, the slope can be 0 for a given interval. So for the second function, as the slope is positive or 0, and once again positive, it's a monotonically increasing function. It's not a strictly increasing function. This function is strictly increasing as well as monotonically increasing. That's for increasing functions. Similarly, you can get the idea for decreasing functions that when a function's slope is strictly negative, it's a strictly decreasing function, or if it's less than or equal to 0, that's a monotonically decreasing function. It's a strictly decreasing function. And obviously for strictly decreasing functions, the slope can be 0 at discrete points. However, if the slope is 0 for a given interval, then it is a monotonically decreasing function. That was increasing and decreasing functions. Two more things to remember are that firstly, if x equals a is a boundary point, you need to check for the one-sided inequality. So let's say that you want to check whether a function is strictly decreasing. What you do is you find f of a minus h, f of a, and f of a plus h. And obviously f of a minus h needs to be greater than f of a, and f of a needs to be greater than f of a plus h. In this case, you can say that the function is strictly decreasing at x equals a. However, if a turns out to be a boundary point, then you only check a one-sided inequality. So you either check this part of the inequality or that part of the inequality, depending on which side is not closed, or rather is not a boundary. The second one is that the function need not be continuous to be monotonic. What does that mean? So let's say you have a function that looks something like that. So the function is discontinuous in this interval. It's still a strictly increasing function, rather it's a monotonically increasing function as the slope is always positive. So that function is still a monotonic function. This approximation is important, of course. So when you use this, basically use this when they ask you to find the value of the function a bit after the value of x. So let's say you know the value of x is at x equals 2 to be 4, and they ask you to find the value of 2.02. Obviously that's a very annoying value. You don't want to substitute 2.02 into the function when you have the value of 2. So what you can do is obviously just write f of x, which is f of 2, that's 4, plus delta x, and delta x is basically 2 plus 0.2, so that's your delta x. So that's 0.02 times f dash of 2, and f dash is the derivative of whatever your function is. And what you'll learn later is actually that these are the first two terms of the Taylor series, and Taylor series is basically an expansion that goes up to many more terms, which you'll later learn in your bachelor's. So anyway, next up we have maxima and minima. Obviously there's something you should know, that the slope at the maxima or minima is 0. So that's a maxima with the slope 0, and that's a minima with the slope 0. And there's two types of maxima and minima, that there's local and there's global. So what's a local maxima or minima? Basically the local maxima or minima is where the slope is 0 in your certain neighborhood in a given interval. Say in a given interval you have something like that, so that's your local maxima, that's your local minima, right? What's your global maximum or minima? And that's basically the maximum or minimum in the entirety of the interval. That's basically like the extrema values. So for a function like that, this is at my positive infinity and a negative infinity, this should be your global maxima, and that would be your global minima. Next we have Rolle's theorem, Lagrange's theorem, and Cauchy's mean value theorem. So in Rolle's theorem, the conditions are that firstly the function f of x needs to be continuous in closed a to b, it needs to be differentiable in open a to b, and f of a needs to be equal to f of b. So we get three cases, which is a concave down, a concave up, and a constant function. In these three cases we have f of a equals to f of b, and the function is continuous in closed a to b, and is differentiable in open a to b in all three cases. So what Rolle's theorem states is that when you have these three conditions satisfied, there will be a point x in the interval a to b such that the slope at x is equal to 0. So this should be x in the first condition where the slope is 0, and this is the x in the second condition where the slope is 0, and in the third case the slope is 0 throughout the function. That's Rolle's theorem. And in Lagrange's mean value theorem, the conditions are that f of x needs to be continuous in closed a to b and differentiable in open a to b. Then Lagrange's theorem states that for some c in the interval a to b, the slope of c is equal to f of b minus f of a over b minus a. Cauchy's mean value theorem has the same conditions, that the function needs to be continuous in closed a to b, differentiable in open a to b, and the slope of x, rather the slope of g at x is not 0 in any value of x in the interval a to b, right? So when these three conditions are satisfied, we could say that f dash of c over g dash of c is equals to f of b minus f of a over g of b minus g of a. So you can also arrive at this from Lagrange's theorem basically. So f dash of c would be this, f of b minus f of a over b minus a, and g dash of would be this. And when you divide these things just sort of get cancelled, and you get this one, Cauchy's mean value theorem. Few more things that you could keep in mind are that when you add two increasing functions, you get an increasing function, and when you add two decreasing functions, you get a decreasing function. When you're subtracting a decreasing function from an increasing function, you arrive at an increasing function, and vice versa. Let's say we have f of x and g of x, two differentiable functions. Let's say f of x has the local maxima at x equals b, and g of x has the local max at x equals f of b. So the obvious thing to state would be that for g of f of x, the local maxima would be at x equals to b, right? Similarly, for if the x equals b is a minima, so if f of x has a local minima at x equals to b, and g of x has a minima at x equals to f of b, then g of f of x would have a local minima at x equals to b. That's basically two things to keep in mind. These two things are important for both mains and advanced, and especially for advanced, this is very important. And another thing to remember would be that when you have something like this, modulus of x minus a plus modulus of x minus b, modulus of x minus c, in this order that a is less than b is less than c, then the minima would be at x equals b, right?